Okay, write the electron configuration for calcium and sulfur atoms and their most probable ion. Okay, so for the calcium one, we're Ca, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And so we know it's 4s2, it's in the fourth row, it's in the s block, and it's in the second row in the s block. So what's calcium's most common ion? Plus 2. Losing 2 electrons, plus 2. So it's going to be, so we'd write calcium with a plus 2 charge here. And then when I write this, what am I going to end up with? Yep, I'm going to end up with the last noble gas we hit, which was argon. So there should be 18 electrons there, and we should have an argon atom. So then I got a sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. And sulfur's most common ion would be what? -2. It's going to gain 2 electrons. And so then we're going to be 1s2, 2s2, 2p6, 3s2, 3p6. So these two things are, yeah, they have the same electron configuration just because they're proximity. So they're both going to end up trying to look like argon. Okay. If a molecule is polar, what's occurring? What types of molecules can be polar and which cannot? Okay, so what's happening when I have a polar molecule?
They have positive and negative and possibly corresponding, but irregular, asymmetrically.
How about you okay with that? Uneven sharing of electrons causing a partial positive and partial negative portion or portions of the molecule. What types of molecule can be polar? It's an uneven sharing, right? So what kind of a molecule can't be polar? How about ionic? Why? No, they don't have shared electrons. There's no sharing in ionic. It's a full-fledged transfer. There's not uneven sharing. There's a transfer of the electron. And how about the covalent? Why is it that the covalent can be? No. They don't transfer. They share. The covalent molecules are sharing. The non-covalent molecules are not sharing. So which one of those could be unevenly sharing? The only one that's doing any sharing, right? So my covalents could be polar. My ionics can't be polar. They're past polar. Polar just means partial positive and partial negative, and the ionic means full-fledged plus charges and minus charges. There isn't any partial sharing because there isn't any sharing happening at all. Okay, so for it will depend on the electronegativity number to determine if you're even talking about something that's polar or non-polar, or sorry, ionic or covalent. Yep. What's the easiest way to know if I'm looking at an ionic compound? There's metal present. If there's a metal there, then I'm looking at an ionic compound, and I don't have to worry about polarity because it won't be polar. And your other option would be if there's a polyatomic ion there. But regardless, you're looking at things that are ionic. Draw the Lewis structure and explain why each is polar or non-polar. Okay, so the electron or Lewis structure, I've got 4 electrons plus 3 times 1 plus 7. So I've got 14 electrons to deal with for my fluoromethane. And so who would you put in the middle? when you have this the structure. I'll put carbon in the middle because it can make the most bonds. Put a hydrogen there and a hydrogen there and a hydrogen there, and I'll put a fluorine there. Does it matter where I put that fluorine? Not in the least, right? So literally, I'm just looking at the molecule as it's shown. I mean, this is a box of tissues, right? I'm still looking at a box of tissues, right? So if that F was up top, all I did was rotate the molecule. It doesn't make the molecule any different. How many electrons have I used so far? I used 8 of my 14, so I have 6 left. Anybody happy? Hydrogens, absolutely. Anytime I got a hydrogen making a bond, they're happy. Anybody else happy? The carbon, right? It's got C's 2, 4, 6, 8, so its octet is satisfied. The fluorine is definitely unhappy, and so let's go ahead and use my other 6 electrons, and there you go. There's your Lewis structure. Is this guy polar or nonpolar? So what do you need to figure out now? This electronegativity is 3.9, and this electronegativity is 2.5, something pretty close to 2.5. So tell me about these 2 electrons right here when the atoms are connected to have a difference of electronegativity of 1.4. Can pull much, much more towards the fluorine. Absolutely. So what we end up having is this side over here being partially negative, and this whole side of the molecule is going to be partially positive. So this molecule is going to be polar for sure. So now the other question is, does it mix with water? Yeah, because water is polar. Okay. How about this next one? So I've got 5 plus 3 times 7, so 26 electrons to deal with. Who do you want to put in the middle? Can you give me 2 reasons why we'd want to put the nitrogen in the middle? How about 3 reasons? It's the odd man out, right? Which one of these is not like the other? So there's one reason. Nature loves symmetry. If I put one of the iodines in the middle, then, and that would not be symmetrical. What's the real chemical reason though? No. Where's the iodine on the periodic table? Second to last column, right? So that column typically wants to make how many bonds? 1. It only needs to make 1 bond so it can look like the neon. So it doesn't make any sense to put it in the middle and force it to make 3 bonds. And the nitrogen, where is it? 3 away. So how many bonds does that mean? 3. So it makes total sense to put that nitrogen in the middle. So I'll go ahead and throw the nitrogen down, and an iodine, and an iodine, and an iodine. Is anybody happy? Nobody's happy. Okay, that's fine. We've used 6. I have 20 electrons left to make people happy. So what do you want to do? Sure. 6, 12. I've used 18 electrons of my 20 that I had remaining. So I have 2 electrons left. All the iodines are satisfied with an octet. I have 2 electrons left. What do I do with them? Give them to the nitrogen. So now my nitrogen is fat, dumb, and happy. Everybody's got 8 electrons. Okay. Yeah, go for it.
Where did you get the 3 times 7?
Since the iodines are in the 7th column, they have 7 electrons. And so there are 3 of them. So that means I have 21 electrons, valence electrons to work with from the iodines alone. And since the nitrogen is in the 15th column or the 5A column, it's got 5 electrons.
So, you said that the iodine needed to gain an electron to become like neon.
No, iodine in this case is going to look like xenon. Oh, did I say neon? Oh, I think I just said noble gas. Yeah. Okay, so this one's harder. What's the reason this one's harder?
It follows the octet rule.
No, the other one followed the octet rule. This follows a Vesper rule, which we went over, but we didn't go over it for a very long time. And the thing that I handed out to you today is us going over Vesper a lot. So can you tell me how many things are connected to the central atom? 6? This is what we're going to do. That's one thing. That's one thing. That's one thing. And that's one thing. So there's 4 things connected. And what's that shape look like? If I'm a central atom and I have 4 things around me, I need to get them as far away from each other as possible because they're surrounded by electrons, or they are electrons. What shape do I form? Tetrahedral. So I'll have a nitrogen in the middle. I'll put the lone pair of electrons up top. I'll put an iodine over here. And we haven't quite talked about this yet, but that's okay. There's my tetrahedral shape. So, now what? What did we do last time to determine if it was polar or nonpolar? What do we have to check? Check the electronegativity numbers. Okay, so the nitrogen is 3.0, and my iodine is what? 2.66? 2.66. Is it really 3.0? Okay. So what's going to happen with, say, these electrons right here? They're mildly pulled. These electrons are going to be mildly pulled towards the nitrogen. And these two? Same thing, right? And these two? Same thing, right? So normally I would say that 0.34 difference in electronegativity isn't big enough, but what I actually have is they sum up. Does that make sense? So I've got that 3.4, 3.4, 3.4, that's actually turns out to have a lot of electronegativity of the electrons moving up this direction. So this side of the molecule is going to be negative, and the other side of the molecule is going to be positive. And so this guy's going to be polar, and yep, he's going to be able to mix with water. Do you remember what the shape of this molecule is going to be? The Vesper shape, including the lone pairs of electrons, are going to be tetrahedral. But do you remember what it was without the electrons? If I were to take a picture of this with X-ray crystallography, then I wouldn't see the electrons. They wouldn't show up. They would be too small and invisible. So what I would see are the 4 atoms that I have there, the nitrogen and the 3 iodines. What'd you say, Gideon? I think it sounded right. It's definitely a pyramid. It's trigonal pyramidal because pyramids are supposed to have 4 sides and this one only has 3. So since there's a lone pair of electrons, I kind of ignore this thing that's at the top, and then I just, well, what's left? It's a triangle, but it's not flat. It's elevated, and an elevated triangle is trigonal pyramidal. Which of the electrons violate the octet rule? In what way do you each violate the rule? Is this rule certainty or a possibility? Okay, so which atoms do we have that can violate? Boron and aluminum and phosphorus and sulfur. So how do the aluminum and boron violate the rule?
They want 6.
Only want 6 electrons, not 8 electrons. And this one's set. This is not a possibility. This is how it is for those 2 atoms.
Why is it like that for those?
If you look at their position on the periodic table, you've got them 3 away And so what they're really looking to do is lose 3 electrons or make combinations with the 3 electrons that they already have. And it's a violation of a rule. And what did you tell us last time about violations of rules? We don't understand exactly what's going on. We only kind of understand what's going on. Okay, so the phosphorus, what happens here? Can have more than 8 electrons, not set. So it could be more than 8, but it doesn't need to be more than 8. But if I have too many electrons, I can force the electrons onto the phosphorus and the sulfur, and they'll accept it. The reasoning behind that is in that third row, that tells us we're in energy level 3. So that means there's an S sublevel, a P sublevel, and a D sublevel. The D sublevel is completely empty. There are no electrons in it at all. So if I start shoving electrons on it, I actually have a place to put the electrons. So they could fit into that completely empty 3D. And that's so far what we got. When I say we, I mean humans.